So thanks everyone for coming to my talk. So I'm going to talk about fine-grained average case hardness, and this is a joint work with Andrea and Virginia. Okay. So just again to confirm, you can see the slides changing, right? You can see my new slide now. Okay, good. So let's just start by defining our goals. We want to understand how hard our problems are on average, and we want to give explicit distributions over which we believe they are hard. And so basically the approach that people use in fine-grained complexity is that there are these core problems that people believe that they are hard, and when they want to prove that a problem P is hard, what they do is that they reduce one of these core problems to the problem P. And you can see a list of these core problems on the left. And what we want to do for proving average case hardness is essentially similar. So we want to start with a core problem and reduce it to the average case of our problem P. So this is basically the approach that we're going to use. And before diving more into the previous work and our results, I want to quickly define K-clique problem because I'm going to mention it a lot. So the K-clique problem says that given an unweighted graph, return true if it has a K-clique as a subgraph and false otherwise. And K-clique hypothesis says that K-clique problem requires n to the omega of K time. And another thing to note is that a lot of the times we use the counting version of these problems. And for example, counting K-clique asks you to return the number of K-cliques in a graph. Okay. So I'm going to list all the previous work that used this simple approach that I mentioned a couple of slides ago. So let's just start with Bolato's paper. So what they did was that for several problems like counting K-cliques, counting orthogonal vectors, counting zero K-clique, etc., they reduced worst case P to average case F sub P, where F sub P is a polynomial that represents P, meaning that if you treat the input of P as a 0, 1 vector, then and you give it to F sub P as like the input, then P and F sub P basically produce the same output. And so, for example, what they do for counting K-cliques is that they reduce worst case counting K-clique to worst case computing F sub K-clique. And then they have this nice self-reduction lemma for polynomials with some constraints that gives them this reduction from worst case computing F sub K-clique to average case computing F sub K-clique. Then Goldreich and Rothblum take this one step further, and they essentially give a worst case to average case reduction for counting K-cliques over a specific distribution, which is a non-uniform distribution, but they end at basically average case counting K-cliques. And then in last year's FOCS, Boat-Serra, Brennan, and Bressler give a worst case to average case reduction for counting K-cliques on Erdős-Renyi graphs. So kind of like the uniform distribution now. And I'm going to refer to this last paper as BBB's paper because, yeah, I'm going to just reference them a lot. And so all of these works, they have a lot of different and nice ideas, which are actually not really specific to the problem that they are working on. And so what we do is that we gather all these ideas and generalize them to produce a framework for proving average case hardness. Okay, so our first result is this average case hardness framework. So for that, we define this notion of good low degree polynomials, or short form GDLP, where we say that if a problem P has a good low degree polynomial, then there is a self-reduction from its worst case to average case on uniform distribution with success probability 1 minus 1 over polylog n. And then if we plug in like counting K-cliques, well, we can see that counting K-cliques has a good low degree polynomial. And then because of like basically it fits in the framework, and we get the same result as BBB's paper. And furthermore, we also show that counting any subgraph on K nodes is also hard. It doesn't just need to be K-clique. Any other subgraph is also hard on average to count with the same success probability. And this was mentioned as an open problem in BBB's paper. So we have this framework. Then what we do is that we introduce this class of problems. We call them factored problems. And we show that they have good low degree polynomials. And so we basically say that they are actually average case hard. So now we have this class of problems that are average case hard. And then we reduce the problems, we reduce these factored problems to other problems to show that, to basically get hardness for other problems, like, for example, counting regular expressions or longest common subsequence and some other problems. And two things to note here. One is that the success probability in all of these average case hardness results is 1 minus 1 over polylog n. And the distribution for this last bullet point, it's like for these reductions, these hardness results are not necessarily on uniform distribution, but they are on an easy to sample distribution. So now I'm going to define quickly the good low degree polynomials and our main theorem for the framework, and talk a little bit about the reductions that I mentioned in the last bullet point. Okay. So we say that a problem P has a good low degree polynomial f sub P if f sub P correctly represents P basically, if it is low degree, meaning that its degree is little o of log n over log n, and if it is a strongly departite. And by that, we mean that the set of variables is divided into d sets, and each monomial has exactly one variable from each set. So that's the definition of being departite. So then we have this theorem that is basically our framework. So suppose that the problem P has a good low degree polynomial, and suppose that there is an algorithm that takes as input an n-bit vector with IID 0, 1 bits taken from a Bernoulli distribution. So this is our random input. And suppose that this algorithm correctly solves P on 1 minus 1 over polylog fraction of inputs, and suppose that it runs in Tn time. So suppose that we have this average case solver for P. Then there is a randomized algorithm that solves P on any input with probability 2/3 and runs in order n plus Tn time. So basically, this is our worst case algorithm. And this is our worst case to average case reduction here for problems that have good low degree polynomials. So this is the main theorem of our framework. Then, as I mentioned, we define these factored problems, and we say that they are hard on average. And then the rest of our results are like this figure. So what we do is that we start with some core problem, and then we reduce that core problem to some factored problem. And then we use our framework to reduce that factored problem from its worst case to average case. And then we reduce the factored problem to our problem P that we want to prove hardness for. So this is basically the flavor of our results. And to show you a map of our reductions, so this is basically all the reductions that we have. There are a lot of problems here, but the things to note is that the problems on the right that are green, they are the core problems. You can see Seth, threesome, KOV. And then the problems in orange are the factored problems that we use as the middle step. And then the problems in white, they are the problems that we prove average case hardness for, like edit distance, KLCS, counting regular expressions, and some other problems. So I want to end this with talking a little bit about future directions of average case fine-grained complexity. So from last year's FOCS, that BBB's paper was published this year, there has been 3 independent works building on that paper. One was our paper, one is Hirahara and Shimizu's paper on average case complexity of biclic under Ceph, and one is Goldreich's paper on for counting k-clicks mod 2. And all these papers were independent, building on BBB's paper. And this kind of shows that there are still a lot of space to explore in average case fine-grained complexity. Yeah, thanks for listening. And I'm going to take any questions now.
Yeah, thanks to speaker Mina for her excellent talk. We have plenty of time for questions. Okay, I have one question here. So your main research says that if the problem has low degree polynomial and some satisfies some property, then the reduction holds. What about the converse? If the problem has a high degree polynomial, then do you suspect that, the problem, I don't know, what do you have?
Yeah, so
Yeah.
I mean, actually, the reason that we defined these factored problems was that a lot of problems, when you try to write them in polynomial form, they have high degree polynomials. And we didn't know how to actually make a low degree polynomial for them. So what we did was like, we created these like factored problems, and then we used reductions from those guys to prove hardness for other results. So that's right. Like our framework, doesn't work for problems with high degree just directly. And like, that's actually a nice question to like provide something that actually works for problems with high degree polynomials.
Thank you. Okay, there's one question on chat. There's a question from Benny on what's the Bernoulli parameter, polylog n over n?
The Bernoulli parameter can basically, I mean, it can be anything. Like, yeah, you can even like take it 1/2. That's like the standard one, for example. But yeah, there is really no restriction on that. It should be just some constant, yeah.
Okay, I hear no more questions. Okay, let's thank the speaker again. Yeah, so we have some time, like about 2 or 3 minutes before the second talk. So let's wait a bit. So I assume that Winchan is, you're the speaker, right? Yeah.
Yes.
Yeah, and then maybe you can start sharing your screen if you're ready, and we can start on time.
Can you see my screen?
Yes.
Good.
Okay, so next, Winchan Hugh will present his work, joint work with Virginia Williams on monochromatic triangles, triangle listing, and APSP.
Hi. Hi, everyone. Thanks for being here. I'm Yinzhan. I'm very happy to present my joint work with Virginia, monochromatic triangles, triangle listing, and APSP. So let me first define O-address monochromatic triangle. In this problem, we are given an n-node graph G, where each edge in the graph has a color. We need to determine for every edge G, whether it appears in a monochromatic triangle in G or not. So that's a triangle where all three edges share the same color. In this example, the only monochromatic triangle is the triangle 1, 2, 3. So we need to answer yes for all three edges on it. And at the same time, we need to answer no for all other edges in the graph. The best known algorithm for O-address monochromatic triangle runs in O tilde into 3 plus omega over 2 time, where O tilde has polylogarithmic factors and omega denotes the square matrix multiplication exponent. And this algorithm was given by Vaslavska, Williams, and Euster. On the lower bound side, if we assume the three-sum conjecture, then no algorithm can achieve O into 2.5 minus epsilon time for positive epsilon. And this result was given by Lincoln, Pollack, and Vaslavska, Williams. So essentially, in the world when omega is 2, and if we assume the three-sum conjecture, then the current algorithm is optimal. Okay. So our paper roughly consists of 2 sets of results. Let me first tell you the relationship between monochromatic triangle and some triangle listing problems. So previously, the reduction from three-sum to O-address monochromatic triangle goes through this intermediate problem called O-address sparse triangle. So in that problem, we are given an image graph G, and we need to determine for every edge E in the graph whether E is in a triangle. So notably, in this graph, the edges do not have colors. So the previous reduction first reduces three-sum to multiple instances of O-address sparse triangle, and then pack all these instances together to one single O-address monochromatic triangle instance. Here, set disjointness and the set intersection are 2 problems that are strongly related to the O-address sparse triangle problem. So even though these 2 problems were originally defined on sets, we can also interpret them as problems on graphs. So roughly, set disjointness is a problem where we are given a tripartite graph on vertex set A union B union C, and we need to decide whether each edge between part A and part B is in a triangle. Here, it's essential that sizes of A and B and C can be different, and the edge set between each parts can be sparse rather than a complete tripartite graph. So similarly, for the set intersection problem, we are given a tripartite graph on vertex set A union B union C, and we need to list a certain number of triangles in the graph. These 2 problems were also known to be three-sum hard, shown by Hopalovitz, Petty, and Porat. And people have used these 2 problems as a hardness sources that are three-sum hard, and prove a lot of problems that are also three-sum hard, including dynamic maximum matching, dynamic ST reachability, and many more problems. Our main contribution is noted by the red edges here. So we essentially replace the three-sum hardness result of O-address sparse triangle, set disjointness and set intersection with a stronger exact triangle hardness. What's good about this is that previously it is known that exact triangle is harder than both three-sum and APSP. So now with our new reduction, all these problems at the bottom, including O-address monochromatic triangle, dynamic maximum matching, dynamic ST reachability, are not only three-sum hard, but they automatically get APSP hardness as well. And this is our first set of results. So now let me tell you about intermediate problems. The notion of intermediate problems was first given by Lincoln, Pollack, and Vaslavska Williams when they were studying the relationship among a set of problems whose running times are all O tilde into 2.5 when omega is 2, but their run times can be different with the current value of omega. And they call such problems intermediate problems. Examples include the all-edges monochromatic triangle problems we are studying, and the max-min product problem, where we are given two n by n matrices A and B, and we need to compute a matrix C, where Cij is defined as the maximum of minimum Aik Bkj over all possible values of k. And the current best algorithm for max-min product also runs in n to the 3 plus omega over 2 time, given by Duan and Petty. Another example is the unweighted directed APSP problem, whose current best algorithm is Zwick's algorithm. So our second result relates many other intermediate problems to the all-edges monochromatic triangle problem. So we say it's related because this is a reduction, but whether it works depends on the value of omega. So it's noted by the dashed arrow here. The key idea in the reduction is to define a new problem called all-edges mono-equal triangle. So intuitively, in this problem, we are also required to answer whether each edge is in a valid triangle or not. But here, a valid triangle needs to have all three edges share the same color, but at the same time, two of the edges have to share the same value, where value is another attribute associated with each edge in the graph. Let me first explain this solid arrow. Okay. We show that suppose there exists a Tn time algorithm for all edges monochromatic equality triangle, then there also exist all tilde Tn time algorithms for all of the following intermediate problems, including the max-min product problem and the unweighted directed APSP problem. So this is a reduction that always works, and it essentially shows that this newly defined all edges mono-equal triangle problem is harder than many other intermediate problems. So now let me explain the trickier dashed arrow. We show that if all edges monochromatic triangle has an O tilde n to the 3 plus omega over 2 minus epsilon time algorithm for some epsilon between 0 and omega over 2 minus 1, then this new problem, all edges mono-equal triangle, also has an O tilde 3 plus omega over 2 minus delta time algorithm for some non-negative delta. And moreover, if epsilon is positive, then delta is also positive. So let me interpret this theorem in two ways. First, in the case when epsilon is 0, then the precondition of the theorem basically says that if there is an algorithm that runs in n to the 3 plus omega over 2 time for all edges monochromatic triangle, which is essentially known. And the consequence of that is that we have an O tilde n to the 3 plus omega over 2 minus delta time algorithm for all edges mono-equal triangle. But since epsilon is 0, our theorem does not guarantee delta is positive, so delta could be 0. And essentially, this case says that all edges mono-equal triangle also has an O tilde n to the 3 plus omega over 2 time algorithm. So essentially, it's another intermediate problem. The case when epsilon is positive is more interesting. So if epsilon is positive, it means that we can improve the current best algorithm for all edges monochromatic triangle by a little bit. And then that means we can also improve over the 3 plus omega over 2 barrier for all edges mono-equal triangle. And by our previous reduction from many other intermediate problems to all edges mono-equal triangle, it means that all these other intermediate problems will also have an algorithm of such running time. So the most interesting one is a max-min product, so whose current best runtime is still n to the 3 plus omega over 2. And this theorem says that if we can improve all edges monochromatic triangle, then we can also improve max-min product. But the limitation of this theorem is this omega over 2 minus 1 upper bound. So in the world, when omega is 2, epsilon essentially has to be 0 in this theorem. So it won't imply any lower bound result like that. And it will be interesting to see how to remove this upper bound limitation here. And thank you for listening. And I'm happy to take any questions.
Okay, then let's thank the speaker again. So there's one question on chat. Can your result be extended to mono-odd cycle?
It's a good question. Let's see. Yeah, I think if we start from like exact k-cliques, then we can get something for mono-odd cycle, probably, but I haven't tried that yet. Yeah, it's an interesting question, and I don't know the answer for sure, but maybe we can use our result. Maybe you can use our techniques for that as well.
Any more questions? Comments?
What are the sizes of the sets of colors and values?
Sizes of the sets, and so let's see. So it really depends on, because the set disjointness problem and set intersection, they inherently can have a lot of parameters, like the size of the vertex sets and the density of edges. So yeah, I think our reduction works. You can vary the sizes of each part of the vertex, but the density of edges on all three parts must be the same. It's like it's like, yeah. So the edge density between A and B and C, C and A must be the same. Yeah.
Okay. Any more questions? Okay, I hear no more. Let's thank the speaker again for his excellent work and talk. Are you the next speaker? Vaishali? Vaishali, you're the next speaker, right?
Yeah.
Can you please share? You start sharing your screen. Yeah. Okay, ready. Yeah, we'll start in 2 minutes. Okay, good. Let's wait a couple of minutes.
Yeah.
Okay, next year, Vaishali will present her work on parameterized approximation scheme for min k-cut. It's joint work with Daniel and Sakin.
Hi, today I'll be presenting my work on the min k-cut problem, and this is joint work with Daniel Akshnal and Sakit Saurabh. Okay, so firstly, we'll start by defining the min k-cut problem. And here we're given an edge-weighted graph along with an integer k as input. And the task is to partition the vertex set of the graph into k non-empty parts. And we refer to this as a k-cut. The goal here is to minimize the total weight of edges that cross the partition. So if this graph was unweighted, then the goal is just to minimize the number of edges that cross the partition. And also observe that if the graph was unweighted and k equal to 2, then this is just the min cut problem. Yeah. So let's go into our results. So our main result is a 1 plus epsilon approximation algorithm that runs in time k over epsilon to the k poly n time. So what this means is that if you're given a graph G and an integer k, yeah, our algorithm in the given time finds a k cut whose weight is no more than 1 plus epsilon times the weight of an optimum k cut. Yeah. And also observe that the exponent of n does not have any dependence on k or epsilon. Therefore, this is an FPT approximation scheme or a fixed parameter tractable approximation scheme. Along the way, we also obtain an exact algorithm for unweighted graphs that runs in time cut size to the power k time. Yeah. So what this says is that if you're given an unweighted graph, an integer k and an integer s, and you're asked the question, okay, does your graph have a cut of size s? Yeah, then you can answer this question with an yes or no in the given time. Also, our results are both optimal up to ETH and constants in the exponent. So basically, the form of the function of both the functions is the best you can do. But what one can try to improve is to improve the polynomial factors or the constants in the exponents. Okay, so now let's briefly look at the history of the problem. So this problem has been well studied in the past and has received a lot of attention in the past few years. This problem is known to be NP complete, and there were 3 groups of different researchers who gave independently gave 2 approximations for this problem, and Saran and Vazirani were the first among these 3 groups. So this greedy algorithm is very simple. So you iteratively keep picking the best min cut in the graph until you have k components. That's all. And they further proved that this simple greedy algorithm is in fact a 2 minus 2 by k approximation. So what is the next direct question? We can ask, okay, can we improve this approximation ratio of 2? But then it turns out the answer is no. And Manurangsi proved a few years back that there is no 2 minus epsilon approximation in polynomial time, assuming small set expansion hypothesis. Okay, from the exact algorithm's point of view, Goldschmidt and Hoffman started this direction of research with an n to the k squared time randomized algorithm, followed by Kargar and Stein, who gave n to the 2k randomized algorithm. And this algorithm is very simple. You just keep contracting edges until there are only k vertices left in the graph. So later, Thorup gave a deterministic algorithm that matched this runtime. Yeah. So what this algorithm does is it finds a polynomial family of spanning trees such that if you take any optimal k-cut, the number of edges, cross edges in this k-cut, there is a tree in this family such that the number of cross edges from this partition in the tree is at most 2k minus 2. And this is very useful, and this is called as Thorup tree packing, and we use these Thorup trees in our algorithm as well. Another direct question is whether you can get an FPT algorithm when parameterized by k, and it turns out the answer is no. So Downey, Eswil Castro, Fellows, Brito, and Rosamond showed that there's no n to the little o of k time algorithm for this problem under ETH. Okay, so what all the results that we saw until now can be viewed as the prehistory of this problem. Because this problem has received a lot of attention in the past 10 years alone, and that too mainly in 4 directions. The first one is to improve the constant of n to the 2k in the exponent of the exact algorithm as far as possible. The second one is to bound the number of minimum k-cuts. So the Kargar-Stein algorithm gives a bound on the number of k-cuts to be n to the 2k for free. So what is the best bound that you can obtain? That's the second direction. Third direction is parameterized approximation with K as the parameter. This is a natural question to ask, and this is where our work lies. This because we know that there is no better than 2 approximation in polytime by Manurangsi's results, and we also know that it is W1 hard when parameterized by K. So okay, the natural question is how much best can you approximate in FPT time? And the last direction is a parameterization with a different parameter, which is the cut size. Okay, for the first two directions, Gupta, Lee, and Lee kickstarted the second innings of this problem with an n to the 2 omega by 3k algorithm, exact algorithm, where omega is the matrix multiplication constant. Later, Lee improved the runtime to n to the k, and they also bounded the number of min cuts to be n to the 1.98k. And very recently in 2020, they obtained the bound for the number of min cuts to be n to the k, and this is essentially tight. So why is the last result is really interesting, mainly because they reanalyzed the Kagas-Stein algorithm and proved that it in fact runs in n to the k time, thus obtaining a bound plus an algorithm. So this essentially closes the first two directions of research. And for one more direction that I told you was parameterization by the cut size. And this direction was begun by Kawabaishi and Thorup in 2011. They gave an S to the S time algorithm. But here, they introduced a very useful notion, which we also use in our algorithm, called unbreakability. So they didn't formalize it, but they used it first. So, and this notion is used in all the following algorithms parameterized by the cut size, and in particular in ours as well. So Chitnis et al. In 2016 improved the runtime to S to the S squared, and they formalized the notion of unbreakability. Later, Sigan et al. Gave the current best, which is S to the S in 2018. So we use some techniques of Sigan et al., but in order to get a better runtime, we merge it with Thorup trees and other concepts to get a better runtime. Okay, so one interesting open problem in this area is whether there is a 2 to the S algorithm. And another interesting open problem is probably there's no 2 to the little o of S algorithm for this problem. Yeah. So let's come to the part that our work lies in, and this is parameterized approximation. Again, the three of them gave a 1.99 to the 9997 approximation in FPT time, and they again improved their own work to 1.81 approx, and they gave an approximation scheme. But note that this is not an FPT approximation scheme, and this is an n to the k time approximation scheme. Later, Kawabaishi and Thorup in 2020 gave a 1.67 approximation in FPT time. And here the open question was, okay, how far can you go in FPT time? So what is the best approximation one can do in FPT time? And so, and that is what we solve in this paper. So if to summarize the past 10 years, 3 directions of research, first, second, and fourth, have essentially been closed. The fourth one still has the open question that I told you. And the third, we closed the third direction by giving an FPT approximation scheme. Okay, so now let's look at our proof ingredients. So there are mainly 3 proof ingredients that went into our algorithm. The first one is a sparsification procedure. So this is very similar to cut sparsifiers, but in the sense that we do not want to bound the number of edges, but it's enough for us to bound the size of opt in the resulting graph. Yeah. And the second one is a polynomial time tree decomposition with 2 properties. So the first property is that, so for those of you who are familiar with tree decomposition, so in the tree decomposition, intersections of 2 bags are called adhesions. And the property that we want here is we want small adhesions and we want unbreakable bags. I'll come back to what unbreakable bag is in a few minutes. And the third ingredient is the main technical core of this paper, which is an S to the K time exact algorithm. So what we do is we do a dynamic programming over the polynomial tree over the tree decomposition we obtain in the second step. Okay, so now this the methodology used is very similar to that used in the S to the S algorithm of Sigan et al. There also they develop a tree decomposition with unbreakable bags and small adhesions, but in their paper they do not. We have like weaker structural guarantees. They wanted an S to S comma S unbreakable bag, but theirs takes S to the S time to find the tree decomposition, but we find it in poly time. So let me quickly tell you what is an unbreakable bag. So basically what intuitively unbreakable bags mean is you take any cut in the graph and impose it on a bag. Okay, so now most of the, if your bag is big, most of the vertices in the bag should lie in one component. So basically, like if you view the superimposed superimpose the cut on this bag, most of the vertices should lie in one big component. There's only one big component and the remaining are small. So that's how it will look. And like how we manage to get down the runtime from S to the S to S to the K is that to bound the DP states, we use Torup trees, and that is how we are able to do it. So to conclude, we had an FPT approximate problem, and we also had we gave an exact algorithm for unweighted graphs. And one interesting open question is in this area is whether there's a 2 to the S algorithm. Thank you.
Okay, thanks for your nice presentation. Any questions? Okay, there's a question on Zoom chat. So what's the constant in the exponent of n in your algorithms?
Oh, in the exponent of n, so I'm not sure. It is quite big. I know because like we use splitters and stuff where the where we have interior algorithms that has constants hidden already, so we just express it as this. But yeah, it's quite big. It's not very small. Yeah. Yeah, so one interesting thing here is that like for those of you who don't know about tree decompositions, so tree decompositions are usually useful for being of small tree width, right? But here, like the tree decomposition that we obtain and which have been used in this, this research of min K-cut, so mostly they've been dependent on this unbreakability and small adhesion size, and this is a nice direction to look at, like rather than only focusing on small necessity of small tree width.
So I have a question. So are there problems where which are parameterized by addition? Like, is addition a good parameter to think about?
Oh, that's a good question, but I'm not aware of whether it has been like adhesion has been used as a parameter. Yeah, but that's a nice way to look at it, I guess. Yeah.
Sorry, Karthik, can you please repeat your question again? So I didn't hear that.
Yeah, so one of the ingredients, so the way they run their DP is by saying the addition size is small in the tree decomposition. Addition is the intersection of a bag with its parent. And that's the key aspect to control the size of the DP. So in a sense, they're not using that the bag size is small, but the addition size is small. So the question was whether one can think of addition as a parameter in the FPT literature. Are there other problems where addition is a parameter?
I see. Thank you. Okay, so let's thanks the speaker again. And then I think next talk will be given by Karthik, right?
Yeah.
Okay. So, maybe you can start sharing your screen, Karthik. Okay, let's start again. So next talk will be given by Karthik on hypergraph K-cut for fixed K in deterministic polynomial time. This is joint work with Chandra Chekri.
Right. Thank you, Sanjay. Yeah, this is joint work with Chandra Chekkuri. Let me begin by introducing hypergraphs. A hypergraph is specified by a vertex set and a collection of hyperedges. A hyperedge is a subset of vertices. If every hyperedge has at most 2 vertices, then the hypergraph is simply a graph. So hypergraphs generalize graphs. In this work, we are interested in hypergraph k-cuts. A subset of hyperedges is said to be a k-cut set if it crosses a k partition of the vertex set. A k partition of the vertex set is a partition of the vertex set into k non-empty parts. And a hyperedge is said to cross a partition if it intersects at least 2 different parts of the partition. In this example, here is a 3 partition. The red and orange hyperedges cross this 3 partition. So the red and orange hyperedges together form a 3-cut set. In the hypergraph k-cut problem, we are given a hypergraph and a fixed constant k. Think of k as 2, 3, 4, 5, and so on. It is a fixed constant that is independent of the size of the hypergraph, independent of the number of vertices. And we would like to find a k partition of the vertex set with minimum number of crossing hyperedges. I'm focusing on the cardinality version for the sake of simplicity. Everything is applicable to the weighted version as well. There are both practical as well as theoretical motivations to study this problem. It turns out that this is a special case of the much more general submodular k-partition problem. I won't go into the definition of the submodular k-partition problem, but it suffices to say that we do not know the complexity of this problem. This is still open. We do not understand it very well. And hypergraph k-cut, in this sense, acts as a nice bridge between the very well understood graph k-cut problem and the not so well understood submodular k-partition problem. So we would like to study this bridge as a step towards understanding submodular k-partition. Graph k-cut, as I just mentioned, has an extensive literature. It was shown to be solvable by Goldschmidt and Hochbaum. It's solvable in deterministic polynomial time. And here n is the number of vertices and k is a fixed constant. So running times of the form n to the k squared would be considered as polytime. Ever since the first work of Goldschmidt and Hochbaum showing that graph k-cut is solvable in polynomial time, the complexity of hypergraph k-cut has been open. And there has been some partial progress towards this question in the literature. The first interesting case that one would want to solve is hypergraph 2-cut. One can solve hypergraph 2-cut, global min cut in hypergraphs, if we can solve min ST cut in hypergraphs. It's a nice exercise to see that min ST cut in hypergraphs can be solved in deterministic polynomial time, which means hypergraph 2-cut is solvable in deterministic polynomial time. There are also alternative algorithms for hypergraph 2-cut, and there are also other special cases of hypergraph k-cut which admit polynomial time algorithms. For the most general case, there are 2 randomized polynomial time algorithms which were discovered in the last couple of years. Both of them are based on random contraction, which does not extend to submodular k-partition. And moreover, both of them are randomized algorithms. So it's natural to ask if we can get deterministic polynomial time algorithms for hypergraph k-cut. And that brings us to the main result of this work. We give a deterministic polynomial time algorithm to solve hypergraph k-cut. And the main technique underlying our deterministic algorithm is to use min ST cuts to recover the parts of an optimum k partition. To tell you a bit more about this technique, I will make 2 simplifying assumptions on the input hypergraph. Firstly, I will assume that all cut values in the input hypergraph are distinct. This ensures that min ST cut is unique for every choice of S and T. And secondly, there exists a unique optimum k partition, which I will denote as V1 through Vk. And these assumptions can be relaxed with more careful tie-breaking rules, but we worked under these assumptions to figure out the details, and I'll use these assumptions for the sake of simplifying the talk. Okay, to recover the parts of an optimum K partition, we show a clean structural result. Here's the structural result. We look at the optimum K partition, V1 through Vk. This is unique, look at it. Now let's focus on an arbitrary part of the optimum K partition, say V1. We show that for every subset T that is disjoint from V1 and intersecting each of V2 through Vk, there is a subset S inside V1 of small size, of size at most 2k minus 2, such that the minimum ST cut is exactly V1 bar. This structural theorem was not known even for graphs. There is a structural theorem for graphs which closely resembles this one. Let me contrast our structural theorem with the one known for graphs. The structural theorem for graphs was shown by Goldschmidt and Hochbaum. Their structural theorem crucially requires that V1 is the part with cheapest cut value. Whereas our structural theorem does not have this assumption, and in a sense, we had to prove this more general structural theorem to be able to solve the hypergraph K-cut problem. So our structural theorem holds for an arbitrary part. There is nothing special about V1. But since our structural theorem aims to recover an arbitrary part of the optimum K partition, the bound on the size of S that we get is weaker than the one in Goldschmidt and Hochbaum structural theorem. And our bound of 2k minus 2 is in fact tight for our structural theorem. Let me quickly flash how to use the structural theorem to get a deterministic algorithm for hypergraph K-cut. The structural theorem allows us to enumerate a polynomial-sized family of subsets containing all parts of the optimum K partition. Here is how you would do this. You initialize the family F to be empty. Now for each subset S of at most 2k minus 2 vertices and each subset T of k minus 1 vertices, you compute the minimum ST cut UU bar and add U to the family. Now by the structural theorem, this family F contains V1. Why does it contain V1? Well, consider applying the structural theorem to the set T that has exactly one vertex from each of V2 through Vk. The size of T is k minus 1, and the structural theorem guarantees that there is a subset S of size at most 2k minus 2 such that minimum ST cut is exactly UU bar. So V1 will be in the family. Since the structural theorem holds for an arbitrary part, all of V2 through Vk will also be in the family. And what is the size of the family? The size of the family is n to the order k. And the time to compute the family is n to the order k min ST cut computations. Recall that min ST cut in hypergraphs can be solved in deterministic polynomial time. So the runtime of this procedure is deterministic polynomial time. With these observations, here is the simple algorithm. Enumerate this family F using this procedure. Now consider all possible K subsets of the family that form a K partition and return the cheapest. And the correctness of the algorithm follows from the fact that the family F contains all parts of the optimum K partition. And the runtime is the time to compute the family plus the size of the family choose K, which is n to the order K squared. Right, in the interest of time, I won't go into the proof of the structural theorem. Let me wrap up. The main contribution is the structural theorem showing that min ST cuts can be used to recover the parts of an optimum K partition. The runtime of the resulting algorithm is n to the order K squared min ST cut computations. We also give a better structural theorem, which leads to a faster runtime. Now the runtime is n to the 8k min ST cut computations. In terms of open questions, can we improve this deterministic runtime? Can we improve the randomized runtime? That is also open. Can we enumerate all min k cuts in hypergraphs in deterministic polynomial time? We do know how to do this in randomized polynomial time. Can we do this in deterministic polynomial time? And going back to the motivation, can we resolve the complexity of submodular K partition for fixed constants K? All right, I'll stop here. Thank you very much for your attention.
Okay. Do you have any questions? Here you mentioned that you want, the question is, one of the questions is improve the running time of your deterministic algorithm. It seems pretty fast to me. So what's your target runtime, the ideal runtime?
Ideal runtime, I would guess, is n to the k min SD cut computations.
Hmm.
So the current best algorithm for graph K cut is randomized. It's Kargos-Stein's algorithm. It runs in time n to the k.
I see.
Can we match this for hypergraph K cut? Even in the randomized case, we don't know.
I see. Thank you. Okay.
Amir asked, can you say a few words about what is the better structural theorem? Okay, yeah, I can. So the better structural theorem, let me quickly flash this. The stronger structural theorem is the one at the bottom. Essentially, instead of recovering one part of the optimum K partition, you try to recover the union of half of the parts of the optimum K partition. So you try to recover V1 through Vk over 2 as a union. And turns out you can do this, and then you can do this with small sized S and T, and then you recurse on the two sides of the hypergraph. That's the idea. It's basically divide and conquer. Instead of trying to find one part one after the other, you try to find half of the K parts.
I have a question. We have like a Karger-Stein in graphs works in n power k time, right? And if you have hypergraphs of bounded like edge size, say it's some delta regular, then before this it was known that like before the Karger-Stein algorithm was reanalyzed, it was known that it was n to the 2 delta, right? So 2 delta k. If you say delta is delta regular. So I'm just asking, like, can you now say so it's like n to the delta k? Do you think that is true? The 2 goes away even in the hypergraph case.
In fact, I believe you can even remove the delta. So you're thinking of delta as the rank of the hypergraph, size of the largest hyperedge.
Yeah.
And I believe the same algorithm, similar algorithm as Karger-Stein, runs in time n to the k times f of delta.
Oh, okay.
And f of delta is, it has an exponential dependence on delta. I mean, yeah, one has to do a careful analysis, but we can show this. It's not n to the k, sorry, it's n to the 2k times f of delta. And the question is whether the 2 can be saved, and that we don't know. We're still thinking about it.
Okay, sure. Thanks.
Okay, so Chandra answered one question on chat. Okay, so let's thanks to speaker again. Okay, I guess Sammy, you're presenting, right?
Yep, you got it, Sungjin.
Yeah, so you can start sharing your screen.
Whoops, that's not the right slide. There we go. Okay.
Okay, the next talk will be on scheduling with communication delays via LP hierarchies and clustering. The talk will be given by Sammy.
Cool, thanks, Sungjin. So yeah, this is joint work with Janardan Kulkarni, Thomas Rothfuss, Jakub Tarnowski, and Yihao Zhang. So let me first introduce our problem of scheduling with precedence constraints and communication delays. So first, kind of like a classic scheduling setup, we assume that we have n jobs denoted by the set j, where each job j has processing length p sub j, meaning how many time steps it takes to complete the job once we begin to process it on some machine. And we have m identical machines to process our set of jobs j, and identical here meaning that all machines are equally able and fast at processing the jobs. Our objective here is going to be to minimize make span, or to minimize how quickly all the jobs can be completed. With the inclusion of precedence constraints here, we invoke this like partial ordering given by this bracket here on the job set j, where j is less than j prime with respect to the partial order, then j must be completed before j prime can begin. So we represent this as a DAG, where the vertices are of a set of jobs. So for instance, over here we have like jobs j1 all the way up to j10. And our directed edges here indicate the precedence order. So for instance, j2 is less than j6 with respect to the partial order. I might also call j2 a predecessor of j6 and j6 a successor of j2. So again, that means like j2 has to be processed before we can start to process j6. And then with the further inclusion of the communication delay, denoted by C over here, if j is less than j prime with respect to that partial order, then if j and j prime are performed on different machines, you can only start to execute j prime at least c time steps after the completion of job j. So this is a little bit to unpack. So we'll look at this example here, an example schedule. So we have our 10 jobs. They all have processing length 1. So we just take one time step to complete once they're scheduled. And this communication delay is 3. So for instance, here we have 10 machines, M1, M2, up to M10. This is a feasible schedule of the jobs respecting the precedence constraints and the communication delay. And then this time access here is just indicating the time steps that each job is scheduled and how much time has passed for this schedule. So if you notice here, there's this like idle time on machine 1 between job 5 and job 6. And the reason that we have to insert this here is because of this communication delay. So if you look at J2 and J6, and you look at the DAG of them, J2 is less than J6 in our partial order, but they're performed on different machines. So from our communication delay constraints, what that's going to mean is that after J2 is finished, we have to wait 3 time steps before we can begin to process J6. On the other hand, like J7 and J3 are successor and predecessor, but since they're performed on the same machine, there's no delay incurred since they're on the same machine. So moving on, we care about communication delays because they're modeling like the delay of transferring information between processors. So you can think of like what happens when the output of one job is the input of another job and there's latency in transferring that information. This occurs in several settings, relevant in real life and in the scheduling literature. But the point I want to make with these 2 examples is that sometimes the communication delay, C, can be very large relative to the number of jobs. So recall N is the number of jobs, and you can think of C as being like N to some small power. So this could be a problem then if C is so large when you're scheduling, if you're not being careful for how to account of that communication delay. We was very open for this problem in terms of like hardness and approximation. There's like order C approximations just using old greedy algorithms. And hardness, we don't know much better than like small constants. So thinking of when C is large, these 2 bounds are extremely far apart. In fact, the quest of finding a constant factor approximation algorithm for this scheduling with communication delays problem was placed on this top 10 open problems in scheduling theory list, like a couple decades ago. And even more recently on like the updated list, it was still considered not understood at all and almost completely open by Nikhil Bansal. And I will just say that, part of the reason why people thought we had no idea what was going on is a lack of promising LP and SDP relaxations for the problem, as opposed to like the instances when the communication delay is small. So when the delay is large, we just really didn't know how to model this as an LP or SDP at all. So today I'm here to talk about some progress. In our work, we show a randomized log C, log M approximation algorithm for this problem. So you can always think of M, the number of machines, and C, the communication delay, as being less than N, the number of jobs. So this is like a log N squared approximation in the worst case. So today I'd like to walk you through like an overview of our algorithm for this. And then right after I talk, there's going to be another talk about like a very similar result. A group of authors find this polylog approximation algorithm for this communication delay problem as well. But their techniques are extremely different, and they actually focus on the duplication setting for job scheduling. So be sure to stay for their talk as well. So I'm going to go into this main result, this algorithm. But first, let me quickly say that we can make some simplifying assumptions on what we're assuming the input looks like. So with only losing a constant factor, we can assume the jobs have unit size and that we actually have n machines. So as many machines as you have jobs. And instead of trying to schedule within time slots, so like I don't really care that job 2 is going to go on time slot 0. Instead, we're going to care about scheduling jobs into C-length intervals. So instead, I just care that job 2 and job 3 are in like this first C-length interval. Job 6 and job 8 are in this second C-length interval. So like a coarser grained schedule. For LP, I'm going to present it different than we did in our paper, a much like more compact version, easier to digest in a short talk. We'll consider the variables y sub j, j prime, where this is basically indicating the probability that jobs j and j prime are scheduled on the same machine and in the same C-length interval. So going back, for instance, like job 6 and 8 here are scheduled on the same machine and in the same C-length interval. Same for like jobs 2, 3, and 7, same machine, same C-length interval. So that's kind of the grouping that we care about here. With those variables, these first 3 constraints, I'm enforcing like a triangle inequality on 1 minus y, and then some type of like symmetric and identity condition. Altogether, they're allowing us to build this function 1 minus y, which is actually going to be a semi-metric. So we're enforcing these constraints so that we actually now have this semi-metric D on the set of jobs. And this is going to be very important for us because we're actually going to use some like a clustering algorithm from the theory of metric spaces. There's some other constraints I won't talk about, but I do want to introduce this other variable here because I'll refer to it later. This C sub j is the completion time of job j, which is giving us the index of the interval where job j is processed. So the index of that C-length interval. All right, so moving into our algorithm here, we're going to look at the set of jobs J star that have close completion time. So a set of jobs whose call this is the completion time, indicating what interval a job is processed. We're looking for those to be like a 1 over log C factor apart. So looking at jobs with close completion time, we take that set of jobs and we run a clustering algorithm by Kalinescu, Karloff, and Rabbani on this semi-metric space, J star, with that semi-metric D that we built from the LP earlier. So we have this clustering algorithm. We guarantee several nice properties from it. And in particular, then we're able to take downward closed subsets of the clusters that we obtained from that clustering algorithm. So from the algorithm, we got clusters V1 to VK. We take downward closed subsets V1 prime to VK prime, where it's downward closed with respect to the precedence order. So a job is only put in like VI prime if it is with all of its predecessors. Then we schedule the V1 prime, VK prime, like the subsets of those clusters on their own machine. And then are going to repeat this on the set of unscheduled jobs, inserting some idle time between our iterations. So what we're really doing here is accounting for that communication delay between iterations, and respecting precedence constraints by only scheduling those downward closed clusters. And we only have to repeat this, or I'm sweeping some things under the rug, but we really only have to repeat this like log m times. So together, this is what's going to give us our log C log m approximation algorithm. Repeating this over the partition of the completion times given by RLP then allows us to schedule all of the jobs. So again, at a high level, we got a log C log m approximation algorithm. All we really did here was simplify and reduce into some like easier inputs, then build an LP where we were able to get this semi-metric on the set of jobs. We clustered iteratively with that clustering algorithm. And then to actually schedule, we just took downward closed subsets of the clusters, scheduling them all on their own machine. And there's some further questions over here. Otherwise, yeah, thanks for listening.
Do you have any questions? Okay, so there's a question here. One question from Sam is, why is log n incurred in the approximation vector?
Sure. Yeah, so log m is the number of times that we had to repeat this iteratively until, like, you know, with good probability, we're able to schedule all the jobs left on one machine. Yeah. So log m is the number of rounds it takes to schedule the jobs with close completion time.
Can I ask a question?
Mm-hmm.
So would you implement the, I mean, not you personally, but would you recommend someone to implement? Do you think it's implementable? I mean, as far as I see, you have to build some LPs, right?
Yeah. So the LP is not too big here that I show you. Yeah, so what the most expensive thing you're going to do is enforce triangle inequality, right? So that's going to be like n cubed, potentially, like many things. So I mean, that could be that, like, n cubed is pretty big. Maybe you don't want to do that. Depends how. Yeah. I wouldn't want to do n cubed, so probably not.
So maybe quick question. Are there some kind of combinatorial crude approaches that can give some polylog approximation?
That's a good question. Not that I'm aware of at all, and this problem had been open for a while. So in particular, everything's like the crudest thing that was known was like order C approximations. It's not like you can be a little less crude and get like log n to the 10th or something like that. So yeah, ours is like an LP based approach, as is the work that's gonna follow what I say is also an LP based approach. So unknown.
Okay, so actually I want to add one more thing here because I scanned the data paper. So I think the next talk, the next result I think they combined with some unknown result. I think they gave combinatorial algorithm for some special case. So I'm not sure. So let's ask you the question. The authors of the second paper. So I have one more question here. So you mentioned the non-uniform communication delay caused by.
Yeah.
So do you have any candidate LP for that, or is you're completely no idea now? What's this?
Yeah. Okay. So if you let's pretend you wanted to extend our results directly. You look at our LP, you're like, yeah, I can write down this LP with so we're talking about this problem here, this third problem, this non-uniform setting. Yeah. You can write down that problem, and then at least with our techniques, now you immediately have multiple metric spaces that you're or let me say multiple metrics that you're working with on the set of jobs. And so then somehow it'd be you're trying to find clusterings that are good with respect to multiple metrics. So you can write down LPs that make sense, but it's not clear that those LPs are useful for any rounding algorithms that we know right now.
Okay, any more questions?
Okay, I will stop sharing.
I guess that's all. Okay, let's thank the speaker again. Who's the next speaker? David. You can start sharing.
Okay. Should I start?
Let's wait for 1 minute. Okay, the last talk of this session will be given by David. He will give a talk about scheduling precedence-constrained jobs on related machines with communication delay. You can start.
Thanks. Yeah, so title of our paper is scheduling precedence constrained jobs on related machines with communication delay. Excuse me. And this is joint work with Biswar Mati and Rajmohan Rajaraman at Northeastern, Zoya Svitkina at Google, and Aravindan Vijayaravagan at Northwestern. So we're going to sort of build up to this more complicated problem through simpler special cases. So by the end of the session, we should have a really good idea of these kinds of scheduling problems. And then we'll present our main results. So first, we're just going to consider precedence constrained scheduling. So here we're given m machines and n partially ordered jobs. Each job has a size, PV, and this gives the amount of time it takes to execute on any machine. So we also have this precedence ordering. If job U precedes V, then U must complete before V can start in the schedule. And our goal here is to minimize make span, which is the completion time of the last job in the schedule. And we'll be minimizing make span throughout this talk. So this problem can be approximated within a constant factor using a simple list scheduling procedure, and that was proved by Graham. So if we can further complicate the problem by introducing related machines. So here we're given n machines and n different sized jobs as before, but we also have a speed associated with each machine, Si. So the ordering is the same as before. Preceding jobs must be completed before their successors, but we also have the requirement that the amount of time it takes to execute job V on machine I is given by the size of V divided by the speed of I, or PV over SI. So Chudak Shmoy were the first ones to give a logarithmic approximation for this problem, and they used this linear program. So here, variable C captures the make span, SV captures the start time of V. The variable XVI indicates whether or not job V is executed on machine I. And informally, the first constraint states that the make span is at least the completion time of the last job. The second constraint establishes the precedence order. The third constraint states that the make span is at least the total load on any machine. And the fourth constraint just states that all jobs must be entirely executed. So their algorithm solves this linear program and then rounds the solution, assigns each job to a group of machines, and then performs list scheduling on the jobs with the additional requirement that jobs must be placed on their assigned group. And the figure shows an example of a schedule you might get from this sort of group-based list scheduling procedure. And this algorithm gives you a log m approximation for precedence constrained scheduling on related machines. So now we're introducing communication delay. So here, as we saw, we have n machines with variable speed and variable sizes on the jobs. And we have the additional condition that if U precedes V and they're executed on different machines, then there must be at least row time between the completion of U and the start of V. And intuitively, this is the time it takes to communicate the result of U to the other machine where we're executing V. But if they're executing on the same machine, then V can start immediately after U. So these two situations arising from communication delay are shown in the picture. So on the left, we see that if B is scheduled on the same machine as A, then it can start immediately after. But if it's on a different machine, then we have to wait row time before scheduling. And as far as we know, there were no prior results for these two papers for this particular model. So for our main results, we're mainly concerned with a model which allows duplication of jobs, where a job is duplicated if it's executed on multiple machines. And this capability can be helpful when scheduling with delays, as we can see in the figure. So on the left, we have a schedule of A, B, and C without duplication. And here, we can schedule A first and then can schedule B immediately after. But we have to either wait until B is done to schedule C on the same machine, or wait row time to schedule C on a different machine. But on the right, we can see that we can schedule C earlier if we duplicate A on the second machine. And as far as we know, there are no prior results in this model either, though some results have been obtained in special cases. So we're motivating the model with an example from machine learning. So in deep learning, we often want to process large DAGs. And in order to do these quickly, we might use multiple kinds of processors, GPUs, CPUs, etc. So our model rises from these different capabilities of the processors, which is modeled as machine speeds, the distance between processors, which is the delay, the dependence among the jobs, which is the precedence ordering, and in general, this problem is known as device placement. So here we have just several prior and related results in the scheduling literature, and I'll just focus on the communication delay results. So utilizing duplication was first proposed by Papadimitriou and Yannikakis. For finite machines, the only approximation result we had was an asymptotic approximation due to Lepere and Rapin, and we built on their work here. Without duplication, there have been several recent results. One is QP test for O1 identical machines and O1 variable delay by Kulkarni and Tarnowski, and that uses a Shirali-Adams hierarchy. And then, as we saw in the previous talk, paper by Davies, Kulkarni, Rothvoss, Tarnowski, and Zhang presents a log rho log m approximation for identical machines with fixed delay. So our central question is, can we design polylogarithmic approximation algorithms for scheduling precedence-constrained jobs and related machines with communication delay? Our main theorem provides a partial affirmative answer. So we show that given an instance of precedence-constrained scheduling on m machines with delay rho, we can compute a schedule whose makespan is within log m log rho divided by log log rho factor of opt plus rho when duplication is allowed. So the techniques we use are a linear programming relaxation that builds on the one that we saw for related machines above. Though we include several new non-trivial constraints to capture communication delay and duplication. So the main challenge here in formulating the LP was capturing the trade-offs that duplication affords. So on the one hand, duplication sort of allows us to finish jobs earlier by avoiding the need for communication. But on the other hand, if we duplicate too much, then we increase the load on the whole system and makespan increases as a result. So as above, we use this LP to assign jobs to groups of machines. And then we run a combinatorial scheduling procedure, which again has to sort of carefully balance these trade-offs of duplication. And we note that if opt is at least rho, that is, if opt has any communication at all, then our algorithm provides a true approximation. Our second result is concerns the linear program used in our makespan algorithm. We show that for a family of instances, the linear program has an integrality gap of at least omega square root log rho, where rho is at least some sufficiently large constant. The proof of this theorem uses graph expanders and shows an interesting property of these random graphs after edges have been removed. Basically, after removing edges, the graph isn't random anymore. But we show that we can still exploit some properties of the original randomness to derive the theorem. We call this property robust expansion, and it's sort of the basis for this integrality gap result. And this theorem provides the first evidence that constant approximation guarantees might not be tractable with known techniques. Finally, our third result, it bounds or quantifies the benefits that duplication affords. So we show that for any schedule that uses duplication, we can convert it into a schedule on the same instance that does not use duplication. And we occur only log squared and log m factor increase in the makespan. The main technique in this result is a combinatorial ball growing algorithm that selects jobs that are then iteratively scheduled in successive rounds. And one interesting corollary to this theorem is that coupled with our algorithm for makespan with duplication, we can actually achieve a polylogarithmic approximation for scheduling without duplication. So thanks for listening. I'll just finish on this slide where we have some open problems, but I can take questions now.
Yeah, so I want to repeat Chandra's question on your paper. So, so if I understand it correctly, so because you gave a way to bound the advantage of duplication, so combining your result with a known result by Lepere and Rapin on asymptotic overlog and approximation algorithm for scheduling duplication for identical machines. Your algorithm gives actually combinatorial algorithm for identical machines case, right? Is that right?
Yes. Yeah. So
Okay.
for the case where machines are identical, we can give a combinatorial approximation for the case of identical machines without duplication. But not for, if we have duplication, then we just achieve, it's an asymptotic approximation.
So, I mean, I guess, in some sense, the communication delay has to be extremely large for this to make sense, no? I mean, but, in that case, I wonder whether there are other ways of trying to approximate where you identify this large communication edges and cut the DAG or something, which is what the LP is kind of doing, I feel. But it's not probably easy to do that globally.
Right. So yeah, if the whole, if every job, if the whole DAG can be scheduled in less than a communication delay, that's the problem, at least with duplication, that we don't know how to handle. But
is the following case easy if all the jobs are unit and the communication delays are large? Is that easy instance?
No, I think that is a hard instance, because then you're sort of in this problem. You're in the space of trying to find. Basically, you're trying to find sets that you can, like downward closed sets that you can schedule on machines to minimize like the total load on every machine. It becomes, yeah, we're not really sure how to handle this case, but it's something we've thought about.
Okay, thank you.
There's one question. Can you repeat the hard case again? What's the hard case?
Oh, the hard case is if all the jobs, or yeah, if you're allowing duplication and all the jobs can be scheduled in less than one communication phase. So if the communication delay is rho, and all jobs can be scheduled in less than rho time, allowing duplication, that's the case where we don't know. We're not sure about hardness, we're not sure about approximations.
And you don't just mean by your LP, right, David? You mean like optimally?
Yes, yeah.
Yeah, maybe I'll just add. So one way to think about the hard case is there is duplication. Let's assume that communication delay is infinite. So you have to figure out how to distribute the jobs with duplication. So this seems very similar to, actually it seems to be related to sort of a densest subgraph kind of problem, because you'll have to put together so somehow you have to partition these into these sets. So there is a relationship to problems that have been studied before, but anyway, yeah, we could not figure out how to handle that.
Yeah, so that's what thought occurred to me. But then, in some sense, it's a relaxation in the sense that you don't have to have a bound exactly, right? Because it's a scheduling setting. If the densest subgraph was easy, then you'll be able to find those things.
Correct. You're right.
But
Yes.
the converse is it
Yes.
not obvious, right?
Absolutely correct. Yeah, that's correct.
And so what is the, I mean, I hope that we can take a few seconds here because it's the last talk. What is the most interesting special case? I haven't worked in scheduling for a while, but just
sure. So we can view. So you can view each job as a set of. So you're given a bunch of sets. Okay. So view each job as a set of its predecessors. Okay, and you have to. So you're given a bunch of sets of elements, and so each set consists of an element and all the other elements that are predecessors of that element. And you're given M machines. You need to place each set on a machine, and you want to minimize the maximum size of a union of what you place.
Right, so the decision is if we have two jobs that share a predecessor, do we place them on the same machine and not duplicate the predecessor, or is it better to place them on different machines and duplicate that predecessor to achieve?
So, I mean, this is the case when the precedence graph is just a bipartite graph, you're saying, right? Or no, that's not true.
No, this would be for general.
Okay, I'll take it offline. I think I'll think of it.
Yeah, great. Yeah.
Okay, thank you all for your participation, and let's thank all the speakers again.